Look up at the stars tonight. You might recognize a constellation or two, feel a sense of familiar wonder. But what if I told you that everything you think you know about that tranquil, twinkling canvas is just the surface of a reality so bizarre, so overwhelmingly vast, that it challenges the very limits of human comprehension? We are living in a cosmic era of profound discovery, where each new observation from powerful telescopes doesn't just add to our knowledge, it completely shatters our assumptions. The universe we thought was slowly and gracefully expanding is actually accelerating outward at an ever-increasing rate, propelled by a mysterious, invisible force that scientists have named dark energy. This isn't a minor detail, it's a fundamental truth that rewrites the story of everything, from the birth of the cosmos to its ultimate fate. This video is an invitation to journey beyond that familiar night sky. We will explore 20 incredible cosmic phenomena that will shake your worldview to its core. We will venture into regions of space so empty they defy logic, encounter stellar corpses with magnetic fields so powerful they can warp the very atoms of your being from halfway across the galaxy, and confront mysteries like the Fermi Paradox, which asks the haunting question: if the universe is teeming with potential for life, why does it seem so silent? These are not just abstract concepts for astronomers in ivory towers. Understanding these wonders is crucial for anyone who has ever looked up and wondered about their place in the grand scheme of existence. They force us to reconsider what is possible, what is real, and what our role is in this incredible cosmic story. So prepare to have your perspective fundamentally altered. We are about to unveil secrets that have been hidden in plain sight, phenomena that reveal a cosmos far more violent, creative, and strange than we ever imagined. This is more than a list of facts. It is a tour of the universe's greatest mysteries, a journey that begins right here, right now, with the simple act of looking up and daring to question everything you see. Let's begin. Picture our entire galactic neighborhood, a vast collection of stars and planets we call home, caught in a cosmic current we cannot see. The Milky Way is not drifting aimlessly through space. It is being pulled, along with our entire local group of galaxies, at a staggering speed of over 2 million kilometers per hour toward a specific point in the constellation of Norma. This is the Great Attractor, a gravitational anomaly of such immense power that it defies easy explanation. Think of it as a hidden waterfall in the river of space, with countless galaxies caught in its flow. The most frustrating part for astronomers is that this mysterious focal point lies directly behind the plane of our own galaxy, a region so thick with gas, dust, and stars that it's like trying to peer through a dense fog. Our view is obscured by the very stuff that makes up our cosmic home, leaving the true nature of this gravitational behemoth shrouded in mystery. For decades, the leading theory suggested that the Great Attractor is not a single, unimaginable object, but rather an immense concentration of mass known as the Norma Cluster, a rich gathering of galaxies. However, even this massive cluster did not seem to possess enough gravity to account for the full strength of the pull we experience. This discrepancy led scientists to look beyond, to an even larger structure, the Laniakea supercluster. Laniakea, which means immeasurable heaven in Hawaiian, is our home supercluster, a vast filament of over 100,000 galaxies, and the Great Attractor appears to act as its central gravitational point, the heart of this cosmic continent. Understanding this reveals a fundamental truth about our universe. Matter is not spread evenly. Instead, it forms a cosmic web with galaxies clustered along immense filaments, separated by enormous voids. The Great Attractor is one of the nodes where these filaments intersect, a grand central station in the flow of galactic traffic. This relentless tug forces us to confront one of the most profound mysteries in cosmology, the nature of gravity itself on the largest scales. The motion of our galaxy cannot be explained by the visible matter we see through our telescopes. There must be far more mass hidden from our view, exerting its influence. This is a direct piece of evidence for the existence of dark matter, the invisible scaffolding that shapes the universe. The Great Attractor, therefore, is not just a destination, it is a clue. It hints at the hidden architecture of the cosmos, a structure built from something we cannot see, but whose gravitational signature is undeniable. It demonstrates that our local universe is part of a much larger, dynamic system, where galaxies are like leaves floating on a river, guided by currents of gravity flowing from regions of immense density. But if the Great Attractor represents a node of immense density in the cosmic web, our next destination is its polar opposite. Imagine a region of space so profoundly empty, so devoid of matter, that it has earned the chilling nickname the Great Nothing. This is the Boötes Void, a spherical chasm in the cosmos stretching an almost incomprehensible 330 million light-years across. To put that staggering scale into perspective, if you placed our Milky Way galaxy at one edge of this void, it would be like a single grain of sand in the middle of an empty sphere larger than the entire continental United States. Within this colossal volume, astronomers expected to find thousands of galaxies based on our average understanding of the universe. Instead, they have confirmed the existence of only a few dozen. It is a desert on a scale that defies belief. The discovery of the Boötes Void in the 1980s sent shockwaves through the field of cosmology because it directly challenges a foundational idea known as the cosmological principle. This principle states that when you zoom out to a large enough scale, the universe should appear roughly the same in every direction, homogeneous and isotropic. It's the idea that there is no special place in the universe. Your view from any point should be statistically similar, but the Boötes Void is a glaring anomaly. A structure this large and this empty suggests that the universe might be lumpier, more textured, and less uniform than we ever supposed. It forces us to ask a deeply unsettling question. Is this void a rare statistical fluke? Or is it a sign that our understanding of the universe's large-scale structure is fundamentally incomplete? So how does such an immense emptiness even form? One leading theory points back to the very beginning of everything. In the first moments after the Big Bang, tiny quantum fluctuations in density were stretched to enormous sizes by a period of rapid inflation. These ripples became the seeds for all future structure. The slightly denser regions collapsed under gravity to form galaxies and clusters, while the less dense regions evolved into the vast voids we see today. In this model, the Boötes Void could be an exceptionally large underdensity from the infant universe that simply never managed to attract enough matter to form galaxies. Another, more speculative idea involves the mysterious nature of dark energy. Perhaps dark energy began acting more strongly in these underdense regions, pushing matter apart and accelerating the emptying process, effectively carving out these cosmic caverns over billions of years. The existence of the Boötes Void and other large voids like it has profound implications. It tells us that the cosmos has a complex topology, a sponge-like structure of dense filaments and walls surrounding empty bubbles. Our home galaxy does not reside in a random location. We are situated within a relatively dense filament, which is why our night sky is filled with stars. If our solar system had formed inside a void like Boötes, our night sky would be almost perfectly black, with no nearby stars to light it up, and the concept of other galaxies might have remained unknown to us forever. This realization underscores our precarious and special place in the cosmos. We are not just anywhere, we are in a location rich with the matter necessary for stars, planets, and life itself. The haunting emptiness of the Boötes Void serves as a stark reminder of the sheer, overwhelming emptiness that constitutes the majority of the universe's volume. A void so vast it challenges not only our maps of the cosmos but our very understanding of its foundation. From the haunting emptiness of the Boötes Void, we now turn to an object of almost unimaginable density and power. If a neutron star is the universe's ultimate pressure cooker, then a magnetar is that same cooker wound up to a point where the very laws of physics begin to fray at the edges. To understand a magnetar, you first have to picture the death of a very specific kind of star. Not just any star, but a massive one, perhaps 30 or 40 times the mass of our Sun. When such a giant runs out of nuclear fuel, its core collapses under its own immense gravity in a cataclysmic supernova explosion. What remains is a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. But under the right conditions, if the parent star was spinning exceptionally fast and had an incredibly strong magnetic field to begin with, this neutron star is born as something far more extreme, a magnetar. The defining feature of a magnetar is, of course, its magnetic field. We are familiar with magnetism here on Earth. A simple fridge magnet has a field strength of about 100 Gauss. The sunspots on our Sun can reach a few thousand Gauss, but a magnetar's field is on an entirely different plane of existence, measuring in the range of 1,000,000 billion Gauss, or 1 quadrillion times stronger than Earth. The numbers are so vast they become almost meaningless. To grasp its power, consider that if a magnetar were located halfway between the Earth and the Moon, about 200,000 miles away, its magnetic field would be strong enough to erase the magnetic strip on every credit card on the planet. But more terrifyingly, it would literally warp the electron clouds of the atoms that make up our bodies, effectively dismantling the chemistry of life from that distance. This isn't just a powerful magnet, it's a force that alters the fundamental nature of matter and space itself. This unimaginable energy is not static. The magnetic field is under immense stress, constantly twisting and straining the solid, crystalline crust of the neutron star, which is only about 6 miles thick but is tougher than any material known to science. Occasionally, this crust can't take the strain anymore. It fractures in an event known as a starquake. The energy released in this stellar tremor is staggering. In a mere millisecond, a magnetar can unleash more energy than our Sun will emit in 100,000 years. For a brief, blinding instant, the magnetar becomes the brightest object in the galaxy, flooding space with a lethal torrent of X-rays and gamma rays. One such event from a magnetar named SGR 1806-20, which erupted in 2004, actually compressed Earth's upper atmosphere and temporarily disrupted long-range radio communications, even though it was 50,000 light-years away on the far side of our galaxy. We felt the ripple effects of a starquake from a distance that is truly cosmic. The existence of magnetars forces physicists to work at the very frontier of their field. In an environment where the magnetic field is so strong, the vacuum of space itself becomes a strange medium, a place where light is bent, and where empty space can actually become birefringent, meaning it can split light into two beams like a crystal. It's a natural laboratory for quantum electrodynamics, testing how matter and energy behave under conditions we could never hope to recreate on Earth. The very formation of such an intense field is a topic of intense study, often explained by the dynamo model. The idea is that during the chaotic collapse of the stellar core, The incredibly rapid rotation and the convective motion of hot, electrically conductive material act like a gigantic generator, amplifying a pre-existing magnetic field to these mind-boggling levels in a matter of seconds. While magnetars represent some of the most powerful and persistent magnetic forces in the cosmos, their outbursts, as violent as they are fleeting. They are like the brilliant, localized flashes of lightning in a cosmic storm. This staggering display of power, however, is merely a prelude to the most titanic explosions the universe has to offer, events that release more energy in 10 seconds than a magnetar will in its entire 10,000-year active lifetime. If the concentrated fury of a magnetar is a lightning strike, then a gamma-ray burst is the detonation of an entire star. These are the universe's most powerful explosions, bar none. For a few fleeting seconds, a single gamma-ray burst can outshine every star in every galaxy in the observable universe combined. The energy it releases in that brief flash is more than our Sun will generate across its entire 10-billion-year lifespan. It is a flashbulb moment on a cosmic scale, a transient event so brilliant that it can be seen from the very edge of space and time. The story of their discovery is almost as incredible as the bursts themselves. During the Cold War, the United States launched the Vela satellites to monitor for secret nuclear weapons tests, which would produce telltale gamma rays. The satellites did detect flashes, but they weren't coming from Earth. They were coming from deep space, a discovery that was initially met with bafflement and secrecy. It took years for astronomers to accept that these were natural events of unimaginable power originating far beyond our galaxy. We now know these bursts come in two distinct flavors, each with a different, equally violent origin story. The first type, known as long-duration bursts, are the death cries of the most massive stars in the universe. When a star dozens of times more massive than our Sun exhausts its fuel, its core can no longer support itself against gravity. It collapses catastrophically, not just into a neutron star, but directly into a black hole. As it falls, the material forms a swirling, superheated disk around the newborn singularity. The immense gravitational and rotational energy of this system is then focused into two narrow, oppositely directed jets that blast outward at nearly the speed of light. If one of these ultra-relativistic jets is pointed directly at Earth, we see it as a long gamma-ray burst, a flash that can last from 2 seconds to several minutes. It is not a spherical explosion, but a focused beam of pure energy, a cosmic lighthouse whose beam, for a moment, is the brightest thing in existence. The second type, short-duration bursts, are even more fleeting, lasting less than 2 seconds. Their origin is just as spectacular. Imagine two neutron stars, the ultra-dense corpses of dead stars, locked in a final, decaying orbit around each other. For millions of years, they spiral closer and closer, rippling space-time with gravitational waves until they finally collide. The impact is monumental, creating a black hole almost instantly and spewing out a cloud of neutron-rich material. In this incredibly hot, dense environment, a rapid process of nuclear fusion occurs, creating the heaviest elements in the universe, including vast amounts of gold, platinum, and uranium. This event also produces narrow jets, resulting in the short, intense flash of a gamma-ray burst. The confirmation of this theory came in 2017, when astronomers detected both gravitational waves and a gamma-ray burst from the same event, a neutron-star merger in a galaxy 130 million light-years away. It was a landmark moment, proving that these bursts are not just incredible light shows, but cosmic forges where the elements that make up our jewelry and our technology are born. This leads to a sobering and vital question. What would happen if one of these events occurred in our own galactic backyard? The good news is that the directional nature of the jets means we would have to be almost perfectly aligned with one to receive the full force of the blast. The bad news is that if a long-duration burst happened within a few thousand light-years of Earth, and we were in the path of the beam, the consequences would be apocalyptic. The initial flash of gamma rays would bathe the Earth's atmosphere in high-energy radiation, ripping apart nitrogen and oxygen molecules. This would create a smog of nitrogen dioxide, a brown, toxic gas that would blot out the sun, triggering a rapid global winter. The gamma rays would also destroy the ozone layer, leaving the planet's surface exposed to the sun's full ultraviolet radiation for years. It is widely speculated that a gamma-ray burst may have been responsible for one of the major mass extinction events in Earth's distant past, specifically the Ordovician extinction 450 million years ago. The threat is remote, but it is real, a reminder that the universe is not a peaceful place. The study of gamma-ray bursts, however, is about more than just cosmic threats. Because their light travels for billions of years to reach us, they serve as invaluable probes of the early universe. The afterglow of a burst, the fading X-ray, optical, and radio emission that follows the initial flash, acts like a backlight, illuminating the gas and dust in the distant galaxies it passes through. By analyzing this light, astronomers can study the composition and evolution of the cosmos when it was only a fraction of its current age. They are the ultimate time machines, allowing us to witness the conditions that existed when the first stars and galaxies were forming. The sheer power of these events makes them detectable across vast cosmic distances, offering a window into eras of the universe that are otherwise invisible to our telescopes. The fleeting, catastrophic violence of a gamma-ray burst thus provides a unique and precious key to understanding the history of everything, a brilliant flash in the dark that illuminates the secrets of the cosmos. Now, just as we begin to comprehend the staggering energy of gamma-ray bursts, the universe presents us with a mystery that is equally powerful but astonishingly brief. If a gamma-ray burst is a cosmic supernova, then a fast radio burst is a cosmic camera flash, a blast of radio waves that appears and vanishes in the blink of an eye, often lasting just a few thousandths of a second. The story of their discovery is one of modern astronomical detective work. In 2007, a young astronomer named Duncan Lorimer was sifting through archived data from the Parkes Radio Telescope in Australia, searching for distant pulsars. Buried in the observations from 6 years prior, he found something extraordinary. A single 5-millisecond spike of radio energy so intense that it saturated the telescope's receiver. It didn't fit the profile of any known object, and it seemed to have traveled from far beyond our galaxy. This was the first fast radio burst, and for years it remained a tantalizing but solitary anomaly, leaving astronomers to wonder if it was a bizarre fluke or a glitch in the equipment. The true breakthrough came as our radio telescopes became more powerful and our search methods more sophisticated. We began to find more of these bursts, confirming that they were real astrophysical events originating from deep space, often billions of light-years away. But the plot thickened dramatically when astronomers discovered that not all FRBs are one-time events. Some of them repeat. Unlike the cataclysmic explosions that produce gamma-ray bursts, these repeating FRBs come from a single source that flares up again and again, sometimes in frantic, unpredictable clusters, and sometimes with a strange, regular periodicity. One famous repeater, known as FRB 121102, has been observed to erupt hundreds of times. Another, FRB 180916, was found to have a 16-day cycle. It would activate for about 4 days, blast out several bursts, and then fall silent for 12 days before starting the pattern all over again. This repeating behavior was a game changer. It immediately ruled out any model involving a single destructive event like a collision or an explosion. Whatever is producing these bursts is not only surviving the event but is capable of doing it over and over again, pointing to an object with an incredibly robust and energetic engine. So, what in the universe could possibly generate such a sudden, colossal release of radio energy? The leading suspects are the most magnetic objects we've just discussed, magnetars. The theory is that a starquake on the surface of a highly magnetized neutron star, perhaps in a distant galaxy, could release a tremendous amount of energy in a very short time, creating a blast of radio waves. In a stunning piece of cosmic confirmation in 2020, astronomers detected a very bright FRB coming from within our own galaxy, and it was traced directly back to a known magnetar, SGR1935 plus 215. This was the smoking gun that strongly linked at least some FRBs to these extreme stellar remnants. However, the incredible diversity of FRBs, their differing energies, repetition patterns, and locations suggests that magnetars might not be the whole story. There could be multiple ways to make an FRB, perhaps involving neutron stars in binary systems with other stars or asteroids, wherein falling material causes sudden, intense bursts of emission as it impacts the star's surface. The sheer power of these bursts is almost beyond comprehension. In that fleeting millisecond, a single fast radio burst can release as much energy as our Sun does over 80 years. For that instant, the source becomes the brightest radio beacon in the universe, outshining the combined radio light of every star in its host galaxy. But FRBs are more than just brilliant flashes. They are also incredibly useful cosmic tools. As the radio waves travel across the vast intergalactic distances, they pass through clouds of ionized gas, the thinly spread material that exists between galaxies. This material slows down the radio waves very slightly, with lower frequencies traveling a tiny bit slower than higher frequencies. By measuring this spread or dispersion, astronomers can actually count the number of electrons the burst has encountered on its journey. This turns each FRB into a probe, allowing scientists to map out the otherwise invisible distribution of normal matter in the cosmic web, helping to solve the long-standing mystery of where all the atoms in the universe are located. The existence of fast radio bursts is a humbling reminder of how much we have yet to learn. They are ephemeral whispers from across the cosmos, signals that challenge our theories and push our observational capabilities to the limit. Each new detection, especially from the powerful new generation of telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, adds another piece to the puzzle. While the extraterrestrial intelligence hypothesis is a tantalizing thought, the weight of evidence firmly points to natural, albeit extreme, astrophysical processes. These millisecond mysteries demonstrate that the universe is filled with transient phenomena, events that flicker in and out of existence on timescales that are inhumanly fast, reminding us that the cosmos is not just a static picture but a dynamic, ever-changing reality, where some of the most dramatic events are over before we can even fully process that they have begun. After grappling with the fleeting, high-energy mysteries of fast radio bursts, we now turn to a puzzle that is unfolding not in milliseconds, but over decades, a discrepancy that strikes at the very heart of our understanding of cosmic history. Imagine you had two incredibly precise clocks, both designed to measure the same thing, the expansion rate of the universe. You set one clock by studying the faint afterglow of the Big Bang, the ancient light from the universe's infancy. You set the other by observing the brilliant deaths of stars in our modern cosmic neighborhood. You expect them to tick in perfect synchrony, confirming a single, elegant story of cosmic evolution. But they don't. Instead, they give you two different, stubbornly inconsistent answers. This is not a small glitch. It is a fundamental crack in the foundation of modern cosmology known as the Hubble Tension. To understand the depth of this problem, we need to look at the two methods themselves. The first approach, often called the early universe measurement, uses the cosmic microwave background, that fossilized light from when the universe was only 380,000 years old. Satellite missions like Planck have mapped this radiation with exquisite detail, revealing tiny temperature fluctuations that are like a blueprint for the entire cosmos. By plugging these patterns into our standard model of cosmology, known as lambda cold dark matter, we can extrapolate forward in time and calculate how fast the universe should be expanding today. This method gives us a very precise value for the Hubble constant, the number that quantifies the expansion rate. The second approach is more direct. Astronomers use what are called standard candles objects whose intrinsic brightness we think we know. The most famous of these are Cepheid variable stars, which pulsate at a rate directly related to their true brightness, and Type Ia supernova, which explode with a remarkably consistent peak brightness. By observing how bright these objects appear from Earth and knowing how bright they actually are, we can calculate their distance. Combining this with measurements of how fast they are moving away from us, thanks to the redshift of their light, gives us a direct measurement of the current expansion rate. This late universe method, championed by projects like the SH0ES team, has been refined over years with incredible care. The tension arises because these two impeccably crafted methods refuse to agree. The Planck measurement from the early universe suggests a Hubble constant of about 67.4 kilometers per second per megaparsec. This means that for every megaparsec, or 3.26 million light-years of distance, a galaxy is moving away from us 67.4 kilometers per second faster. But the local measurements using supernova and Cepheids consistently point to a faster rate, around 73 kilometers per second per megaparsec. The difference might seem small, only about 5 or 6 kilometers per second, but the precision of each measurement is so high that the gap is statistically significant. It is extremely unlikely to be a simple fluke. This is a direct conflict between our view of the infant universe and our view of the contemporary cosmos. So, what does this mean? The scientific community is essentially divided into two camps. The first possibility is that there is an unknown systematic error, a hidden flaw in one of our cosmic yardsticks. Perhaps our understanding of Cepheid variables is not as complete as we think, or maybe there is some subtle dust in the interstellar medium that is dimming the light from supernova in a way we haven't fully accounted for. Teams are working tirelessly to find and eliminate these potential errors, but so far the discrepancy persists even as measurements become more and more precise. The second and far more thrilling possibility is that the Hubble tension is real, and it is telling us that our standard model of cosmology is incomplete. Our current model is built on a set of assumptions about the contents and behavior of the universe, including the nature of dark matter and dark energy. What if dark energy is not constant, as Einstein's cosmological constant suggests, but is instead evolving over time, becoming stronger and accelerating the expansion more quickly than our models predict? Or what if dark matter has properties we haven't yet discovered, perhaps interacting with itself or with normal matter in a new way? There are even suggestions that a new type of relic particle from the early universe, like a new species of neutrino, could be altering the expansion history in a way that resolves the tension. Each of these ideas points to a need for new physics beyond our current understanding. The resolution of the Hubble tension is arguably the most pressing issue in cosmology today. It is not just an academic debate, it is a crucial test for our entire cosmic narrative. If the discrepancy is due to new physics, it would be one of the most significant discoveries since the realization that the universe is expanding at all. It would force us to rewrite the textbooks and open up a new chapter in our quest to understand the fundamental forces that have shaped everything we see. This fundamental uncertainty about the very fabric of our cosmic reality stands in stark contrast to the next phenomenon, whose destructive potential, while terrifying, is governed by the predictable and unwavering laws of gravity. While the Hubble tension reveals a deep-seated uncertainty in our cosmic equations, the laws of gravity, at least on a local scale, remain brutally predictable and unforgiving. This brings us to one of the most chilling specters in the cosmos, the rogue black hole. We often picture black holes as stationary monsters, anchored at the centers of galaxies or locked in binary orbits with companion stars. But the universe is a dynamic and often violent place, capable of hurling these gravitational abysses out into the great dark like cosmic cannonballs. Imagine a solitary predator, a black hole with the mass of several suns, stripped of its stellar surroundings and set adrift in the interstellar void. It emits no light, gives off no warning signal. It is a perfect engine of gravity moving in utter silence, a ghost sailing through the ocean of space. The creation of such a nomad is a tale of cosmic violence. The most common scenario unfolds during the majestic but brutal dance of galactic mergers. When two galaxies collide, their central supermassive black holes are drawn toward the new galactic core, eventually forming a binary pair. As they spiral closer, a third star or even a smaller black hole can wander too near this gravitational whirlpool. In a complex interplay of forces, one of the black holes can be slingshotted away at tremendous speed, ejected from its home galaxy entirely. This gravitational kick is so powerful that the black hole can achieve escape velocity, destined to wander the intergalactic medium forever. Another mechanism involves a different kind of stellar death. In a binary star system where one star collapses into a black hole, the supernova explosion of its companion can be asymmetrical. If the blast is lopsided, it can act like a rocket engine, kicking the newborn black hole clear of the system, sending it on a solitary path through the galaxy. Detecting an object that is, by its very nature, invisible is one of astronomy's greatest challenges. We cannot see the rogue black hole itself, but we can observe its gravitational signature warping the fabric of space-time around it. The primary method for hunting these ghosts is a phenomenon called gravitational microlensing. As a rogue black hole drifts through space, its intense gravity acts as a temporary lens. If it passes directly between Earth and a distant background star, it will bend and focus the star's light, causing the star to appear to temporarily brighten in a very specific, symmetrical pattern. The duration of this brightening event is a clue to the mass of the lensing object. A brief flash might indicate a planet-sized object, while an event lasting several months would point to the signature of a stellar mass black hole. In 2022, astronomers using the Hubble Space Telescope analyzed 6 years of data and believe they captured the telltale microlensing signature of just such a solitary black hole drifting through our galaxy about 5,000 light-years away. The confirmed existence of even one rogue black hole forces us to confront a startling possibility. Our Milky Way could be teeming with these dark wanderers. Current estimates suggest there could be as many as 100 million stellar mass black holes in our galaxy alone. If even a small fraction of those were ejected from their birth clusters or binary systems, it would mean there are countless invisible masses gliding unseen through the galactic disk. This raises a question that touches on both scientific curiosity and a primal fear. What would happen if one of these rogue black holes passed through our solar system? The good news is that space is overwhelmingly empty, and the chances of such a direct encounter are astronomically small over the lifetime of our Sun. However, if one were to approach, we wouldn't see it coming. The first sign would be subtle gravitational perturbations in the orbits of the outer planets, a slight wobble that would slowly grow into chaos. As it drew nearer, its gravity would begin to tear apart the Oort Cloud, sending a storm of comets inward. If it passed through the inner solar system, the delicate gravitational balance that has allowed life to flourish on Earth for billions of years would be utterly destroyed, likely flinging planets into the Sun or out into interstellar space. It is a remote but sobering reminder of the latent dangers that drift in the darkness between the stars. The solitary journey of a rogue black hole, a single point of immense mass traveling alone, presents a stark contrast to our next phenomenon, where gravity orchestrates a dance of titans on a scale that is almost impossible to comprehend. The solitary journey of a rogue black hole presents a stark contrast to the next phenomenon, where gravity orchestrates a dance of titans on a scale that is almost impossible to comprehend. We now arrive at the cosmic ballet of supermassive black hole binaries. Picture the aftermath of a galactic collision, an event that unfolds over hundreds of millions of years. When two galaxies merge, their central supermassive black holes, each weighing millions or even billions of times the mass of our Sun, are drawn toward the new, combined core of the resulting galaxy. At first, they are separated by thousands of light years, but as they sink through the dense environment of stars and gas, they begin a slow, inexorable gravitational waltz, eventually forming a binary pair locked in a mutual orbit. This dance, however, is fraught with a cosmic traffic jam known as the final parsec problem. As the black holes spiral closer, their gravitational influence clears out the surrounding stars. To get any closer, they need to lose orbital energy. Theory suggests that for them to merge within the age of the universe, they must interact with a third object, perhaps a star or a cloud of gas, to steal its momentum and tighten their orbit. For a long time, astronomers wondered if many of these binaries might stall, perpetually circling each other just a few light years apart. The question became, do they ever actually finish their dance? The hunt for these elusive pairs is a testament to astronomical ingenuity. Since we cannot see the black holes directly, we look for their indirect signatures. One method involves monitoring quasars, the incredibly bright active nuclei of distant galaxies powered by matter falling into a supermassive black hole. If that black hole is part of a binary, the orbital motion can cause a periodic variation in the quasar's brightness, a subtle flicker over months or years as the feeding process is rhythmically disturbed. Another, even more precise technique uses pulsar timing arrays. Pulsars are the universe's most accurate clocks, spinning neutron stars that emit beams of radio waves with metronomic regularity. As a gravitational wave from a distant supermassive black hole binary passes through our region of space, it minutely stretches and compresses space-time, causing the timing of these pulses to vary in a predictable pattern across the sky. It's like trying to detect a ripple in a pond by observing how it affects the rhythm of dozens of floating metronomes. The ultimate fate of these binaries is one of the most violent events in the cosmos. In the final seconds before merger, the black holes whip around each other thousands of times per second, moving at a significant fraction of the speed of light. They churn the spacetime around them into a chaotic froth, emitting gravitational waves so powerful that they carry away orbital energy in a final, furious burst. When they finally collide, they form a single, even more massive black hole. But according to the laws of general relativity, the new black hole cannot contain all the gravitational energy of the final moments. It must ring down, settling into a stable shape by emitting a final burst of gravitational waves, like a struck bell fading into silence. The detection of such waves would be the ultimate test of Einstein's theory in the most extreme regime imaginable. Studying these systems is not just about witnessing cosmic violence. It is fundamental to understanding the life cycle of galaxies. There is a remarkable correlation between the mass of a galaxy's central black hole and the properties of the galaxy's central bulge. This suggests that black holes and their host galaxies co-evolve, each influencing the growth of the other. The merger of two supermassive black holes is likely the climax of this relationship, an event that may inject tremendous energy back into the galaxy, regulating star formation and shaping its future evolution. By finding these binaries, we are watching the engine of galaxy growth in its most active phase. The gravitational waves from such a colossal merger do not simply vanish. They travel outward, carrying their story across the universe and leading us to consider the very medium they travel through, the cosmic background from which everything began. From the intricate gravitational dance of supermassive black hole binaries, we now turn our attention to a much older, far more subtle signal that carries the story of the universe's very first moments. To understand the cosmic microwave background, we have to travel back in time almost 14 billion years, to a point when the universe was not filled with stars and galaxies, but was a hot, dense, expanding fireball. For the first several 100,000 years, it was so hot that light could not travel freely. Protons and electrons formed a searing plasma, constantly scattering photons. But as the universe expanded and cooled, a monumental transition occurred. The electrons and protons combined to form neutral hydrogen atoms in an event called recombination. Suddenly, the universe became transparent, and that primordial light which had been trapped was finally set free. That first flash of light, now stretched and cooled by the subsequent expansion of the universe, fills all of space today as a faint microwave glow, a cosmic background radiation that is the oldest light we can possibly observe. This cosmic microwave background is not perfectly uniform. When satellites like Planck map it with incredible precision, they reveal a tapestry of tiny temperature fluctuations, tiny variations of a few millionths of a degree. These are not imperfections, they are the seeds of all cosmic structure. The slightly denser regions, appearing as slightly cooler spots in the CMB, held the gravitational potential that would, over billions of years, pull in more matter, eventually collapsing to form the galaxies, clusters, and the vast cosmic web we see today. It is the ultimate baby picture of the cosmos, and for the most part, its patterns align beautifully with our standard model of cosmology. But there is one feature that stubbornly refuses to fit the picture, a feature so anomalous that it has sparked debates for nearly 2 decades, the CMB cold spot. Located in the southern constellation Eridanus, the cold spot is not just a little bit cold. It is a significantly larger and colder region than our models predict. It spans a vast area on the sky, about 5 degrees across, which is roughly 10 times the diameter of the full moon. The probability of such a large and cold anomaly appearing by random chance in our standard model is extremely low, less than 1%. This has forced cosmologists to propose 2 very different, equally fascinating explanations. The first, and more conservative, idea is that the cold spot is not a feature of the primordial universe at all, but is instead an effect created by something along the line of sight between us and the CMB. This something is thought to be a supervoid, an enormous region of space with a much lower density of galaxies than average. The theory goes like this. As the light from the CMB travels through the universe on its way to our telescopes, it passes through regions of varying gravitational potential. According to general relativity, photons climbing out of a gravitational well, like a void, lose energy, a phenomenon known as the integrated Sachs-Wolf effect. If there were a truly immense supervoid between us and the cold spot, the light passing through it would be slightly redshifted, making that part of the CMB appear cooler. The problem is, the void would have to be colossal, perhaps hundreds of millions of light years across, to account for the observed temperature drop. Astronomers have searched for such a supervoid, and while some have reported evidence of an underdense region in that direction, its size and emptiness do not seem sufficient to fully explain the cold spot. If it is a supervoid, it would be one of the largest structures ever discovered, pushing the limits of our understanding of how such cosmic emptiness can form. The second explanation is far more radical and captures the imagination like few other ideas in cosmology. What if the cold spot is not an illusion caused by a void, but is a genuine scar from the birth of the universe? Some theories suggest it could be evidence of a collision between our universe and another bubble universe in the multiverse. The concept of eternal inflation proposes that our universe is just one expanding bubble in a much larger, eternally inflating meta-universe. Other bubbles are constantly forming, and if one of these neighboring universes collided with ours in the distant past during the first moments of inflation, the energy released in that collision could have left an imprint on the CMB, a circular bruise like the cold spot. If this were true, it would be the first observational evidence that our universe is not alone, a discovery that would fundamentally reshape our understanding of reality itself. The cold spot, therefore, represents a thrilling fork in the road of cosmic inquiry. One path leads us toward a deeper understanding of the large-scale structure of our own universe, forcing us to confront the possibility of voids so vast they challenge the cosmological principle. The other path leads us to the precipice of the multiverse, a concept that has long been confined to theoretical speculation. Future galaxy surveys will map the distribution of matter in the direction of the cold spot with ever greater detail, hoping to definitively confirm or rule out the supervoid hypothesis. If no sufficient void is found, the multiverse explanation will gain significant weight, turning this faint, cold patch on our sky maps into one of the most important anomalies in all of science. It serves as a powerful reminder that even our most precise map of the cosmos, the CMB, still holds profound mysteries that may point toward physics beyond our current comprehension. This ancient light, a relic of creation, continues to challenge us, whispering secrets about the fundamental nature of everything. The ghostly scaffolding of the cosmos is not built from anything we can see. It is constructed from dark matter, an invisible substance that forms vast, spherical halos around every galaxy and galaxy cluster in the universe. Think of a galaxy like our Milky Way, not as a simple disk of stars, but as a luminous jewel embedded within a much larger, unseen sphere of mass. This dark matter halo is the true gravitational anchor of the galaxy, the hidden framework that holds the entire structure together. Without it, the stars on the outer edges of spiral galaxies would be moving much more slowly, orbiting the center according to the same rules that govern our solar system. But they are not. In the 1970s, astronomer Vera Rubin made a landmark discovery while studying the rotation curves of galaxies. She found that stars far from the galactic center were orbiting at roughly the same speed as those closer in. This was completely unexpected. It was as if the entire disk of the galaxy was rotating like a solid plate, defying the laws of gravity that say the visible mass alone should not be able to hold it all together. The only plausible explanation was that there had to be a huge amount of unseen matter spread throughout a vast halo, providing the extra gravitational pull to keep those outer stars from flying off into intergalactic space. This gravitational signature is not the only way we detect dark matter. Its presence is also revealed through a phenomenon predicted by Einstein's theory of general relativity, gravitational lensing. When light from a distant galaxy travels through the universe, its path is bent by the gravitational fields of massive objects it passes. When the intervening object is a galaxy cluster surrounded by its immense dark matter halo, the effect is dramatic. The cluster acts as a cosmic lens, warping and distorting the images of background galaxies into long, faint arcs and multiple images, like a funhouse mirror on a galactic scale. By meticulously mapping these distortions, astronomers can essentially create a map of the cluster's total mass, both visible and invisible. Time and again, these maps show that the amount of mass required to create the observed lensing is far greater than the mass of all the stars and gas we can see. The overwhelming majority of the mass is dark, confirming that these halos are not a minor component, but the dominant gravitational force shaping the largest structures in the cosmos. So what exactly is this mysterious substance? We know what it is not. It is not made of protons, neutrons, and electrons like everything we encounter in everyday life. It does not interact with light or any other form of electromagnetic radiation, which is why it is completely transparent and invisible. It appears to only interact with ordinary matter through gravity. For decades, the leading theoretical candidate has been a hypothetical particle known as a weakly interacting massive particle, or WIMP. The idea was elegant. These particles would have a mass somewhere between that of a proton and a heavy atom, and they would interact with normal matter only through the weak nuclear force and gravity. This would explain why they are so elusive. For years, physicists have built exquisitely sensitive detectors, often placed deep underground to shield them from cosmic rays, hoping to catch the rare, faint ping of a WIMP colliding with an atomic nucleus. But despite decades of searching, these direct detection experiments have consistently come up empty. Not a single confirmed WIMP signal has been found. This null result has spurred the search for alternative candidates. One particularly intriguing possibility is the action, a particle originally proposed to solve a different problem in particle physics. Actions would be incredibly light, potentially billions of times lighter than an electron, but they would exist in such vast numbers that they could still account for the dark matter. If they exist, they might be detectable through a very subtle conversion into microwave photons in the presence of a powerful magnetic field. Experiments are now underway to hunt for these ghostly particles. Other, more exotic ideas include primordial black holes formed in the early universe, or even particles that belong to a hidden, shadow sector of physics with its own forces and interactions. The frustrating truth is that after decades of brilliant theoretical work and ingenious experiments, the fundamental nature of dark matter remains one of the greatest unsolved mysteries in all of science. What we have learned from sophisticated computer simulations is that dark matter halos are not simple, smooth spheres. They have a rich and complex internal structure. Because dark matter particles are thought to interact so weakly, they do not clump together easily. However, they do feel the pull of gravity. Simulations show that dark matter halos form hierarchically, with smaller clumps merging over time to build larger ones. The result is a halo that is lumpy, containing thousands of smaller subhalos orbiting within it like satellites. These dense knots of dark matter may themselves host their own small, faint galaxies, or they may be completely dark, adding to the gravitational tapestry without any visible component. This intricate architecture, predicted by supercomputer models, is another layer of the dark matter puzzle, a hidden landscape of gravitational potential that we are only beginning to chart. This mysterious, invisible substance that pulls the universe together, providing the gravitational skeleton for all structure, stands in stark opposition to the force we will explore next, a repulsive energy that works on the largest scales to push everything apart. If dark matter is the invisible glue holding the cosmos together, then dark energy is the phantom force relentlessly trying to tear it apart. This is arguably the greatest puzzle in all of modern science, a discovery so profound that it completely upended our vision of the universe's destiny. For most of the 20th century, astronomers understood the universe to be expanding as a consequence of the Big Bang, but they assumed that expansion was slowing down. The collective gravity of all the matter in the cosmos, stars, galaxies, gas, and dark matter, was thought to be acting as a cosmic brake, gradually pulling back on the outward rush of space. The central question was whether there was enough matter to eventually halt the expansion and cause a big crunch, or if the universe would simply coast onward forever, expanding at an ever-decreasing rate. Then, in the late 1990s, two independent teams of astronomers made a shocking discovery that would win them the Nobel Prize. They were using distant Type Ia supernova as cosmic mile markers to measure the expansion rate billions of years in the past. To their astonishment, they found that these extremely distant supernovae were dimmer than expected. This meant they were farther away than our models predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Something was overpowering gravity itself, pushing galaxies apart with ever-increasing force. That something was given a name that reflects our profound ignorance: dark energy. The numbers involved are almost impossible to grasp. Based on the most precise measurements from missions like Planck and the Dark Energy Survey, we now know that the composition of the universe is a recipe for bewilderment. The ordinary matter that makes up everything we can see, every star, planet, and human being, accounts for a mere 5% of the total energy density of the cosmos. Dark matter, the mysterious gravitational scaffolding, makes up about 27%. That leaves a staggering 68% of the universe to be composed of dark energy. Think about that. For most of human history, we were completely unaware of 95% of the universe. And now we find that the dominant component, the force that controls the ultimate fate of everything, is a repulsive energy about which we know almost nothing. It is the ultimate cosmic irony. The force that shapes the universe on the largest scale is also the most elusive. So what could dark energy possibly be? The leading candidate is an idea that Albert Einstein himself proposed and then later discarded as his greatest blunder: the cosmological constant. In the equations of general relativity, Einstein introduced a constant term, represented by the Greek letter lambda, to represent a uniform energy density inherent to the vacuum of space itself. This vacuum energy would have a repulsive gravitational effect, causing empty space to push itself apart. In the context of the static universe that Einstein believed in, this was a fudge factor. But in our expanding universe, it becomes a compelling explanation for dark energy. According to quantum physics, the vacuum of space is not truly empty. It is a seething foam of virtual particles constantly popping in and out of existence. This quantum jitter should endow empty space with energy. The problem is one of the most infamous discrepancies in all of science. When physicists calculate the predicted value of this vacuum energy based on quantum field theory, the result is about 120 orders of magnitude. That's a 1 with 120 zeros after it, larger than the value we observe from cosmic acceleration. This is often called the worst theoretical prediction in the history of physics. If the quantum calculation were correct, the repulsive force would have been so immense that the universe would have torn itself apart before even the first stars could form. The fact that we exist at all suggests that either our understanding of quantum vacuum energy is deeply flawed, or dark energy is something else entirely. This leads to a host of alternative theories. Perhaps dark energy is not a constant but a dynamic field that has changed over the life of the universe, an idea sometimes referred to as quintessence. In this model, the strength of dark energy could have varied, potentially explaining why its influence seems to have become dominant only in the last several billion years. Other, more radical ideas suggest that our theory of gravity itself, Einstein's general relativity, may need modification on the very largest scales. Perhaps what we perceive as a mysterious dark energy is simply a sign that gravity behaves differently over cosmic distances than our current equations predict. Each of these possibilities has profound implications, and astronomers are engaged in a massive effort to distinguish between them by measuring the expansion history of the universe with ever greater precision, using supernova, galaxy clusters, and the large-scale structure of the cosmic web. The true weight of the dark energy mystery lies in what it tells us about the ultimate fate of the cosmos. The properties of dark energy dictate the final chapter of the universe's story. If dark energy is indeed a constant cosmological constant, as current evidence tentatively suggests, then the future is one of relentless and accelerating expansion. Billions of years from now, distant galaxies will be receding from us so quickly that their light will no longer be able to reach us. The observable universe will shrink to include only our local group of galaxies, which is bound together by gravity. The rest of the cosmos will fade from view, leaving our descendants, if any still exist, with a sky that is fundamentally empty, devoid of any evidence that other galaxies ever existed. This is the heat death or big freeze scenario, a cold, dark, and lonely end. If, however, dark energy is something more potent and grows stronger over time, a far more dramatic fate awaits: the Big Rip. In this scenario, the repulsive force would eventually overcome all other forces, first tearing apart galaxy clusters, then galaxies, then solar systems, and finally, in the last instance, ripping apart atoms and the very fabric of spacetime itself. The universe would end not with a whimper, but with a catastrophic shredding of reality. The discovery of dark energy did not just add a new chapter to cosmology, it forced us to rewrite the entire ending, transforming our cosmic story from a predictable deceleration into an accelerating mystery whose final outcome is still hidden in the dark. The accelerating expansion driven by dark energy sets the stage for a finale that is not an explosion, but an inexorable fade to black. This is the heat death of the universe, a fate not of fire, but of ice, unfolding over timescales so vast they dwarf the entire current age of the cosmos. To even begin to comprehend it, we must first understand a fundamental concept from physics: entropy. Entropy is essentially a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Think of it like a hot cup of coffee left on a table. The heat, which is a form of energy, is concentrated in the coffee at first, but it naturally spreads out, warming the cup, the air around it, until everything is the same lukewarm temperature. The energy hasn't disappeared, it's still there, but it has become useless, evenly distributed, unable to do any further work. The universe in its entirety is the ultimate isolated system, and it is following this same inescapable path. In the far, far future, dark energy's relentless push will become the dominant narrative of the cosmos. First, the sky will begin to empty. galaxies outside our local gravitationally bound group will be pulled away by the stretching of space itself, their light redshifted into oblivion. Their images will slow, then freeze, as the photons struggle against an expansion rate that eventually exceeds the speed of light across those vast distances. Within 100 billion years or so, any civilization born in the Milky Way will look out into a black void. The evidence for the Big Bang, the cosmic microwave background radiation, will have been stretched to such long wavelengths that it will be undetectable, its energy diluted to almost nothing. The universe will have effectively erased its own history, leaving future astronomers with no clues to its violent and crowded beginning. The age of stars will also come to a definitive close. All the hydrogen fuel for new star formation will eventually be locked up in dead stars or diffuse gas clouds too far apart to collapse. The last red dwarf stars, frugal with their nuclear fuel, will sputter out after trillions of years. The universe will go dark, illuminated only by the occasional ghostly light of a white dwarf slowly cooling or the final flash of a collision between brown dwarfs. The cosmos will be a graveyard of stellar remnants, white dwarfs, neutron stars, and black holes drifting in an ever-cooling sea of expanding space. But even these dark remnants are not eternal. Over almost unimaginable eons, a process predicted by Stephen Hawking will take effect: black hole evaporation. According to quantum mechanics, pairs of virtual particles constantly pop in and out of existence at the edge of a black hole's event horizon. Occasionally, one particle falls in while the other escapes, stealing a tiny amount of the black hole's mass. This Hawking radiation is incredibly faint for large black holes, but over time it causes them to slowly shrink. A black hole with the mass of our Sun would take around 10 to the 67th years to evaporate, a 1 followed by 67 zeros. The supermassive black holes at the centers of galaxies would take even longer, but eventually even they will vanish in a final, faint pop of particles. This leads to the final state, the heat death. With all useful energy gradients gone, with every region of space at the same, infinitesimally low temperature, just a fraction of a degree above absolute zero, the universe will reach a state of maximum entropy. No more stars will shine, no more planets will orbit, no chemical reactions will occur. It will be a cosmos without change, without structure, without the possibility of any form of complexity or life. It is a silent, static, and eternal equilibrium. This bleak forecast, the Big Freeze, stands in stark contrast to the fiery, creative violence of the Big Bang. It forces us to confront the transient nature of everything we hold as constant. The vibrant, chaotic, and beautiful universe we see today, teeming with galaxies, nebulae, and stars, is not the permanent state of affairs. It is a brilliant but fleeting firework display in the cosmic night. This realization imbues our present epoch with a profound preciousness. We are living in the cosmic spring, a golden age of light and structure, at a time when the universe is still young enough to be dynamic and full of wonder. From the silent, chilling forecast of the universe's heat death, we now journey back to its vibrant, explosive youth, to an era when the cosmos was a chaotic furnace of raw power. In this tumultuous period, the most brilliant objects in the universe blazed into existence: quasars. The name itself, short for quasi-stellar radio source, hints at the initial confusion they caused astronomers. When first detected in the 1950s and 60s, they appeared as star-like points of light on photographic plates, yet their spectra revealed a shocking secret. They were not stars at all, but something located billions of light-years away, receding from us at tremendous speeds. For a single, pinpoint object to be visible from such a staggering distance, it had to be emitting almost unimaginable amounts of energy. We now understand that a quasar is the intensely luminous heart of a young galaxy, a supermassive black hole in its most voracious feeding phase. At the core of every quasar lies a gravitational monster, a black hole weighing anywhere from millions to billions of times the mass of our Sun. But a black hole alone is dark. Its brilliance comes from the frenzied banquet taking place around it. Imagine a vast whirlpool of gas, dust, and even entire stars spiraling inward at near light speed. This swirling maelstrom, known as an accretion disk, becomes superheated by immense friction and gravitational forces to temperatures of millions of degrees. As this material is compressed and torn apart, it glows with a ferocious intensity across the entire electromagnetic spectrum, from radio waves to X-rays. The energy released in this process can outshine the combined light of every single star in the quasar's host galaxy, making it visible across the observable universe. It is a cosmic lighthouse whose beam can pierce through billions of years of cosmic history. Quasars are not just brilliant curiosities, they are fundamental time machines. Because light takes time to travel, when we observe a quasar 10 billion light-years away, we are seeing it as it was 10 billion years ago. This allows astronomers to use quasars as probes to study the era of galaxy formation, a time when the universe was only a fraction of its current age. Their light acts as a backlight for the cosmos. As it journeys for eons towards our telescopes, it passes through clouds of gas and the faint, wispy filaments of the cosmic web. By analyzing the specific absorption lines etched into the quasar's spectrum, the unique fingerprints of elements like hydrogen, helium, and carbon, scientists can map the distribution and composition of matter that lies between us and the quasar. It is like turning on a brilliant flashlight in a foggy room. The beam illuminates every wisp and particle in its path, allowing us to chart the otherwise invisible structure of the universe. One of the most profound mysteries that quasars have helped unveil is the intimate connection between galaxies and the black holes at their centers. There is a remarkable correlation. The more massive a galaxy's central bulge of stars, the more massive its central black hole. This suggests that the growth of the galaxy and the growth of its black hole are deeply intertwined, a process known as co-evolution. The quasar phase is thought to be a critical part of this relationship. As the black hole feasts, pouring out torrents of energy, it can also trigger powerful outflows of gas and radiation. These quasar-driven winds are so forceful that they can blow the remaining gas and dust right out of the galaxy, effectively shutting down further star formation. In this way, the quasar acts as a cosmic regulator. Its brilliant, violent life not only builds the black hole but also puts a cap on the growth of its host galaxy, ultimately determining its final size and shape. The brightest beacons in the universe, therefore, are also agents of cosmic feedback, sculpting the galaxies we see today. This understanding, however, leads to a pressing and still unresolved question. How did these supermassive black holes grow to such colossal sizes so quickly after the Big Bang? We have observed quasars powered by black holes with billions of solar masses existing when the universe was less than 1 billion years old. For a black hole to reach that mass in such a short time is a monumental challenge for our models. They would have had to accrete matter at the maximum possible rate for their entire lives, a process that should have generated radiation pressure powerful enough to blow away the very gas they were trying to consume. This suggests that the earliest black holes might not have started from the collapse of a single massive star, but were perhaps born larger from the direct collapse of enormous gas clouds in the early universe. Or they may have grown through a rapid series of galactic mergers, where black holes combined to leapfrog in size. The existence of these ancient quasars pushes our theories of structure formation to the limit, forcing us to consider more exotic and rapid mechanisms for building the cosmic giants that would go on to shape the evolution of galaxies for billions of years. The intense, brilliant activity of these quasars, which so dramatically shaped their young galaxies, stands in stark contrast to the next phenomenon, a slower, more destructive, but equally creative process that unfolds over the entire lifespan of the cosmos. The brilliant, frenetic activity of quasars highlights a period of intense, centralized violence in the early universe. But galaxy evolution is not just a story of a single, luminous core. It is also a saga of large-scale collisions and mergers that unfold over billions of years, a process so dramatic it has earned the name galactic cannibalism. Far from the serene, isolated islands of stars they appear to be, galaxies are social creatures, often found in groups and clusters where gravitational encounters are inevitable. In these dense environments, a relentless cosmic dance takes place, where larger galaxies use their immense gravity to tear apart and ultimately consume their smaller neighbors. This is not a gentle process. It is a violent, chaotic, and yet profoundly creative force that reshapes galaxies, dictates their futures, and fills the cosmos with spectacular visual evidence of past encounters. To understand how this works, picture our own Milky Way not as a static picture, but as a dynamic system surrounded by a swarm of smaller satellite galaxies, like moons orbiting a planet. The largest of these, the Large and Small Magellanic Clouds, are visible to the naked eye in the southern hemisphere, but there are dozens of smaller, fainter dwarfs. One of them, the Sagittarius dwarf spheroidal galaxy, is currently in the process of being cannibalized by the Milky Way. Our galaxy's far greater gravitational pull is stretching this tiny companion apart, literally sucking the stars right out of it. We know this is happening because astronomers have mapped the sky and discovered vast, faint rivers of stars that arc over the north and south galactic poles. These are tidal streams, the remnants of the Sagittarius dwarf, a cosmic smear of stars tracing the path of its orbit as it is slowly digested. It is a real-time demonstration of galactic cannibalism happening right in our celestial backyard, a ghostly testament to a destruction that began billions of years ago and is still ongoing. The effects of these mergers are transformative. When two galaxies of similar size collide, the result is even more dramatic than a simple ingestion. As they swing past each other, their mutual gravity creates immense tidal forces, pulling long tails of stars and gas out into intergalactic space. These spectacular structures, aptly named tidal tails, can stretch for hundreds of thousands of light years, looking like the antennae of some colossal insect. Meanwhile, the clouds of gas within the galaxies are violently compressed, triggering a firestorm of new star formation known as a starburst. The galaxy becomes a cosmic nursery working at a frantic pace, creating thousands of new stars at a rate that can dwarf that of a quiet galaxy like our own. However, this fertile period is often short-lived. The same gravitational chaos that triggers the starburst also funnels vast amounts of gas into the central supermassive black holes of both galaxies, potentially igniting them as quasars, while also blowing away the remaining gas reservoirs, eventually quenching star formation. The elegant spiral structures of the original galaxies are completely destroyed in this gravitational maelstrom. What remains after the galaxies have fully merged over hundreds of millions of years is often a smooth, featureless elliptical galaxy, a bland sphere of old stars with little gas left to form new ones. This brings us to the most significant galactic collision in our own future. The Milky Way and our nearest large galactic neighbor, the Andromeda Galaxy, are hurtling towards each other at a speed of about 110 kilometers per second. In approximately 4.5 billion years, they will begin their first close pass. What would this look like to a hypothetical observer on Earth? First, it is crucial to understand that the collision of galaxies is not like the collision of two solid objects. Galaxies are mostly empty space. The stars within them are so far apart that it is incredibly unlikely any two stars would actually hit each other. Instead, the interaction is a gravitational one. As Andromeda approaches over millions of years, it would grow from a faint smudge into a magnificent spectacle, eventually filling a large portion of the night sky. As the galaxies begin to swing past each other, their gravitational pull would warp their familiar shapes beyond recognition. The neat spiral arms of the Milky Way would be stretched and distorted into long, luminous streams. The sky would become a chaotic canvas of two intermingling galaxies, with new stars igniting in brilliant blue clusters throughout the turbulent gas clouds. It would be a truly breathtaking, albeit terrifying, sight. After this first pass, the galaxies will swing apart, only to be pulled back together by gravity for a second, and then a final merger. Over the course of 1 or 2 billion years, they will settle into a new, combined galaxy, often nicknamed Milkomda. This new entity will likely be a large elliptical galaxy, devoid of the beautiful spiral structure we know today. The night sky from a planet within Milkomda would be profoundly different. The dark lanes of dust that currently stripe the Milky Way would be gone, having been used up in a final burst of star formation or blown away by the activity of the merged black holes. The sky would be dominated by a vast, diffuse glow of old, red stars, with fewer of the bright, young blue stars we see today. It would be a quieter, more homogeneous sky, the final result of a creative destruction that began billions of years in the past. This large-scale reshaping of galaxies through cannibalism finds a parallel in the life cycle of individual stars, where death on a small scale also serves as a crucial source of creation for the cosmos. The violent, large-scale destruction of galactic cannibalism, which forges new galaxies from the wreckage of old, finds a beautiful and essential parallel in the life cycle of individual stars. It is in the fiery death of a star that the universe performs its most intimate act of creation, transforming simple elements into the complex ingredients of worlds and life. The phrase, "we are stardust," is more than just poetic sentiment. It is a literal scientific fact. Every atom of oxygen you breathe, every particle of carbon in your cells, and every trace of calcium in your bones was forged in the nuclear furnace of a star that lived and died long before our solar system even began to coalesce from a cloud of gas and dust. This profound connection to the cosmos is made possible by one of the most important processes in the universe, supernova nucleosynthesis. To understand how this works, we need to look at the life and death of stars much more massive than our Sun. A star is essentially a balancing act between the inward crush of gravity and the outward push of energy from nuclear fusion. For most of its life, a star fuses hydrogen into helium in its core, a process that provides the stability we enjoy from our own Sun. In more massive stars, this process continues, creating a layered structure like a cosmic onion. Once the hydrogen is exhausted, the core begins fusing helium into carbon, and then carbon into oxygen, and so on, each successive fusion stage creating heavier elements. However, this chain has a limit. The fusion process is a game of energy. It releases energy when light elements fuse together up to a point, but that point is iron. Fusing elements together to create iron actually consumes energy instead of releasing it. So, when a massive star finally builds an iron core, it is building its own tomb. With no energy being generated to support it against the immense force of gravity, the core collapses catastrophically in less than a second. the outer layers of the star, no longer supported, come crashing down at nearly a quarter the speed of light. The impact on the dense core is so violent that it triggers a titanic rebound shockwave, hurling the star's entire outer envelope into space in a supernova explosion. It is in this brief, unimaginably violent event in the heart of the explosion itself that the true magic happens. The conditions become so extreme, with temperatures reaching billions of degrees and neutrons flooding the environment, that elements heavier than iron are rapidly assembled. This process, known as rapid neutron capture or the R process, forces atomic nuclei to gobble up neutrons before they have a chance to decay, building elements like gold, platinum, silver, and uranium in a matter of seconds. The supernova blast wave then acts as a cosmic delivery service, scattering these newly forged elements far and wide into the interstellar medium. This enriched gas, now seeded with a periodic table's worth of heavy elements, eventually becomes part of subsequent generations of stars and planets. Our own solar system formed from such a cloud about 4.5 billion years ago, a cloud that had been fertilized by the deaths of countless stars. The gold in a wedding ring was likely born in the collision of two neutron stars, a different but equally potent source of heavy elements. The iodine essential for our thyroid function was forged in a supernova. The uranium that can power a city or a weapon was created in these stellar cataclysms. This means that the planet we walk on and the very bodies we inhabit are composed of atoms that were once part of stars that died in spectacular explosions, perhaps billions of years ago. This leads to a humbling question: how many stars had to die for us to exist? While we cannot know the exact number, astrophysicists can make estimates based on the composition of our solar system. To account for the abundance of heavy elements found on Earth and in the Sun, it likely required the explosive deaths of dozens, if not hundreds, of massive stars, along with contributions from neutron star mergers, all occurring in our galactic neighborhood over billions of years before the Sun was born. Each of us carries within us the legacy of these ancient cosmic events. Every breath draws in oxygen atoms that were created in a star that lived and died in a far-off time and place, making the universe not just something we look at, but something we are intrinsically, physically a part of. This cycle of stellar death and rebirth is the universe's way of recycling itself, transforming the simple hydrogen and helium of the Big Bang into the rich complexity that makes planets and life possible. The cataclysmic explosion that scatters these vital elements also has another, more subtle, but equally pervasive effect on our world. While the supernova blasts that forge the elements of life are spectacularly visible, they also unleash an invisible torrent of high-energy particles that constantly bombard our planet, a phenomenon known as cosmic rays. This is not a form of light or radiation in the conventional sense, but a genuine rain of matter subatomic shrapnel hurtling through the void. Think of it as a constant, microscopic hailstorm where the hailstones are primarily protons and atomic nuclei, the smashed-up remains of atoms, accelerated to velocities tantalizingly close to the ultimate speed limit of light itself. These particles are the shrapnel from the universe's most violent events, and their journey brings the fury of distant cosmic cataclysms right to our celestial doorstep. The origins of these cosmic projectiles are as varied as they are violent. The majority of the lower-energy cosmic rays that reach Earth are thought to be born in the aftermath of supernova explosions. The expanding shockwave from a dying star acts like a gigantic natural particle accelerator, surfing charged particles on a wave of magnetic fields and plasma, boosting them to incredible speeds over vast distances. But supernova are not the only cosmic engines at work. the active nuclei of distant galaxies, powered by supermassive black holes feasting on matter, can generate jets of plasma that stretch for thousands of light years. These jets are perfect environments for accelerating particles to energies far beyond what any supernova can achieve. Even our own sun contributes, especially during periods of intense solar flares, sending out bursts of solar energetic particles that can pose a risk to astronauts and satellites. This invisible rain, therefore, is a composite message from many different sources, each with its own signature of energy and composition. When one of these high-energy particles, which may have been traveling for millions of years, finally encounters Earth, it does not reach the surface directly. Instead, it collides with the nucleus of a gas molecule in the upper atmosphere, typically nitrogen or oxygen. This collision is so violent that it shatters the atomic nucleus, creating a shower of secondary particles, pions, muons, electrons, and gamma rays that themselves carry significant energy. These secondary particles then collide with other nuclei, creating a cascading avalanche that spreads out as it travels downward. This phenomenon, known as an air shower, can span several kilometers in diameter by the time it reaches the ground. It is these secondary particles that scientists detect with intricate arrays of sensors, allowing them to work backward to determine the energy, direction, and likely identity of the original primary cosmic ray. It is a forensic investigation on a cosmic scale, piecing together the story of a single particle from the debris it leaves behind. The energies involved in these collisions are almost beyond human comprehension. The cosmic rays we detect every day have energies millions of times greater than those produced in the Large Hadron Collider, the most powerful particle accelerator ever built by humans. But even these are dwarfed by the rare, ultra-high-energy cosmic rays, sometimes called "oh my God" particles. The name is no exaggeration. One such particle, detected in 1991 by the Fly's Eye Observatory in Utah, carried kinetic energy equivalent to a well-thrown baseball, but compressed into a single subatomic particle. To have that much energy, a proton must be moving at 99.999999999999995% of the speed of light. The existence of such a particle poses a monumental challenge to physics. What natural process in the universe could possibly act as an accelerator powerful enough to impart such an unbelievable amount of energy to a single proton? This mystery is compounded by a significant problem. Cosmic rays are not reliable messengers of their own origin. Because they are composed of charged particles, their paths are bent and twisted by the magnetic fields that permeate interstellar and intergalactic space. Unlike light, which travels in straight lines, a cosmic ray's trajectory is a tangled, chaotic path. By the time it reaches us, there is no way to trace it back in a straight line to its source. It is like trying to find the origin of a leaf caught in a hurricane by looking at the spot where it finally landed. For the most energetic particles, the oh my God particles, this problem is particularly acute. Their immense energy means they should be somewhat resistant to magnetic deflection, but their suspected sources must be relatively nearby, within our local supercluster of galaxies, because particles with such high energy interact with the cosmic microwave background radiation, losing energy over intergalactic distances. So, the accelerators must be both incredibly powerful and located not too far away, yet we have been unable to pinpoint any obvious candidate sources that match the required energy output. The search for these cosmic accelerators is one of the great quests in modern astrophysics. Scientists use giant observatories like the Pierre Auger Observatory in Argentina, which covers an area of 3,000 square kilometers with thousands of detectors, to catch these rare high-energy events. By studying the pattern of the air showers, They hope to find slight anisotropies, statistical hints that more particles are coming from one general direction in the sky than another. There have been tantalizing correlations with nearby active galaxies or starburst galaxies, but nothing conclusive. The answer may lie in even more exotic phenomena, such as the jets from microquasars within our own galaxy, or perhaps from the decay of hypothetical super-heavy particles left over from the Big Bang. Whatever the source, its discovery would reveal a new class of astrophysical object, one that operates at energy frontiers we can scarcely imagine. This relentless, invisible bombardment is a constant reminder that our planet is adrift in a dynamic and often violent galaxy, a shooting gallery for particles accelerated in events of staggering power. While the cosmic rays bombarding our planet originate from violent events within our galaxy, they are messengers from a realm that is still, in a sense, local. But what of true visitors from beyond, objects that have traveled between the stars themselves? To understand the significance of these interstellar wanderers, we must first journey to the most distant and mysterious region of our own solar system, a place that exists more as a gravitational idea than a visible structure, the Oort Cloud. Imagine the solar system not as ending with the orbit of Neptune, or even with the dwarf planet Pluto in the Kuiper belt, but as a vast, spherical shell of icy debris stretching halfway to the next star. This is the Oort Cloud, a theoretical reservoir of trillions of icy planetesimals, leftovers from the solar system's formation that were scattered outward by the gravitational influence of the giant planets billions of years ago. Its inner edge is thought to begin around 2,000 astronomical units from the Sun, and its outer boundary may extend as far as 100,000 astronomical units, nearly a light year into the void. At such distances, these objects are so frigid and dark, reflecting virtually no sunlight, that they are effectively invisible to our most powerful telescopes. Their existence is inferred from the behavior of long-period comets, those spectacular visitors that swoop into the inner solar system on orbits lasting thousands or even millions of years, their paths suggesting they were gently nudged inward from this distant, frozen deep freeze. For decades, the Oort Cloud remained a compelling but unproven theory, the final frontier of our Sun's gravitational dominion. Then, in October 2017, everything changed. Astronomers at the Pan-STARRS telescope in Hawaii detected a faint object moving at such a high speed that its trajectory could not be bound by the Sun's gravity. It was not from the Oort Cloud, it was passing through it. This was our first confirmed interstellar visitor, an object from another star system entirely. It was given the name Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The discovery was momentous, but the object itself was bizarre. Its light curve, the pattern of how its brightness changed over time, indicated that it was tumbling, and its shape was inferred to be highly elongated, perhaps 10 times as long as it was wide, unlike any known asteroid or comet in our solar system. Even more puzzling was its acceleration as it traveled away from the Sun. While comets accelerate due to the rocket-like effect of sublimating ice, Oumuamua showed no visible coma or tail of gas and dust. This led to a flurry of scientific debate, with some proposing it could be a chunk of solid hydrogen ice or even, in a highly speculative but captivating idea, an artificial light sail from an extraterrestrial civilization. The more likely explanation is that it was a unique type of icy body that released gas in a way that did not produce a visible trail, but its true nature remains an active topic of research, a cryptic postcard from an unknown star system. Just 2 years later, in August 2019, we were gifted a second, much clearer example. An amateur astronomer in Crimea, Gennady Borisov, spotted another object on a hyperbolic trajectory. This visitor, named 2I/Borisov, was unmistakably a comet. As it approached the Sun, it developed a classic coma and a faint tail, confirming that the basic processes of comet formation are not unique to our solar system. Borisov was a familiar sight, a dirty snowball that could have been a cousin to comets like Halley. Spectroscopic analysis of its light revealed it was rich in carbon monoxide, a composition that suggests it formed in a very cold region of its home planetary system, perhaps far from its parent star. The fact that we detected 2 such visitors in just 2 years suggests that interstellar objects are not rare anomalies, but are likely constantly drifting through our solar system. Current estimates suggest there could be thousands of Oumuamua-sized objects within the orbit of Neptune at any given time, most too faint and fast for us to detect with current technology. Our solar system, rather than being an isolated island, is more like a busy crossroads in the galactic flow, with traffic passing through all the time. The profound implication of these visitors is that they are pristine samples from other star systems. Every rock in our solar system has been altered by billions of years of exposure to the Sun's heat and radiation. But an object like Borisov, which spent millions or billions of years in the deep freeze of interstellar space, is a frozen time capsule from the moment its parent planetary system formed. By studying its composition, we are, for the first time, directly analyzing the building blocks of a world orbiting another star. This allows us to perform comparative planetology on a galactic scale. Do other planetary systems form from the same mix of ices and rocks as ours? The initial evidence from Borisov suggests both similarities and intriguing differences. Future missions are already being planned to intercept the next interstellar visitor. With advanced warning, we could send a spacecraft to fly by, or even land on, one of these objects, providing a direct, hands-on analysis of material from another star. The data returned would be invaluable, telling us not just about the object itself, but about the conditions in its native nursery, offering clues about the commonality of planetary formation throughout the Milky Way. The existence of a vast Oort cloud around our Sun, and the passage of objects from similar clouds around other stars, fundamentally blurs the boundary between our solar system and the wider galaxy. It suggests that planetary systems are not completely closed environments. Through gravitational interactions, stars can fling trillions of comets out into the galactic disk and in turn capture those ejected from their stellar neighbors. This means that material is being exchanged between star systems on a constant basis. In the early history of the solar system, it is even possible that such interstellar interlopers could have delivered water or organic compounds to a young Earth, raising the tantalizing possibility that the seeds of life itself could have hitched a ride on a rock from another star. The discovery of Oumuamua and Borisov has opened a new chapter in astronomy, transforming interstellar space from an empty void into a highway filled with celestial drifters, each carrying a unique story from a distant, unseen world. As our ability to detect these faint, fast-moving objects improves, we can expect a steady stream of new messengers, each one offering a fresh glimpse into the diversity and architecture of planetary systems far beyond our own. The ability to step onto the surface of a distant world without ever leaving Earth is one of the most extraordinary achievements of modern astronomy, and it all hinges on a simple but powerful principle: light carries fingerprints. When an exoplanet passes directly in front of its host star from our vantage point, an event known as a transit, a tiny fraction of the star's light filters through the planet's thin atmospheric fringe. By capturing this sliver of light with powerful telescopes like Hubble and more recently the James Webb Space Telescope, astronomers can break it down into a spectrum, a rainbow of colors that holds the chemical signature of the atmosphere. Each gas leaves a unique barcode of dark lines, absorbing specific wavelengths of light. The presence of water vapor, for instance, shows up as a distinct pattern, while methane or carbon dioxide creates its own telltale marks. This technique, called transmission spectroscopy, transforms a distant point of light into a complex chemical profile, allowing us to sniff the air of worlds trillions of miles away. The ultimate goal of this atmospheric detective work is the search for biosignatures, combinations of gases that could potentially indicate the presence of life. On Earth, our atmosphere is wildly out of chemical equilibrium, and that disequilibrium is a direct product of biology. The large amount of oxygen, which is highly reactive and should quickly disappear by combining with rocks and gases, is continuously replenished by photosynthesis. Similarly, methane produced by microbes persists alongside oxygen, a combination that would not last long without constant biological renewal. Finding a similar imbalance on a rocky exoplanet within its star's habitable zone, the region where temperatures could allow for liquid water, would be a monumental discovery. Imagine a spectrum revealing the simultaneous presence of both oxygen and methane, or detecting a smog of complex organic molecules that have no plausible abiotic origin. Such a finding would suggest that something on that world is actively manipulating its atmosphere, a tantalizing hint that we are not alone. However, this search is fraught with complexity and the constant risk of false positives. The universe is a creative chemist, and many processes that have nothing to do with life can produce gases we associate with biology. For example, oxygen can build up abiotically through the breakdown of water vapor in a planet's upper atmosphere by intense ultraviolet light from its star. Methane can be released by volcanic activity or serpentinization, a reaction between water and certain types of rock. A planet like Venus shows us that a thick atmosphere of carbon dioxide can create a runaway greenhouse effect, rendering a world in the habitable zone utterly uninhabitable. This means that a single gas is never enough. The true challenge is not just detection, but interpretation. Astronomers must become planetary detectives, looking for contextual clues. They must understand the nature of the host star. Is it a calm, stable star like our Sun, or a volatile red dwarf prone to flares that could strip away an atmosphere? They must consider the planet's geology and potential for volcanic outgassing. A convincing biosignature will likely require a cocktail of gases in proportions that are difficult to explain without biology, a signal that stands out against the background noise of planetary geochemistry. This is where the James Webb Space Telescope has ushered in a revolutionary new era. With its massive gold-coated mirror and sophisticated infrared instruments, Webb is uniquely equipped to analyze the atmospheres of smaller, Earth-sized planets. Its early observations have been breathtaking, already detecting water vapor, sulfur dioxide, and a variety of other molecules in the atmospheres of gas giants and smaller mini-Neptunes. While these worlds are not themselves candidates for life as we know it, these observations prove the telescope's exquisite precision. The next step is to turn this power toward the most promising rocky targets, like those in the TRAPPIST-1 system, 7 Earth-sized worlds orbiting a cool red dwarf star. Webb is now gathering the data that will allow us to ask the most profound questions about these distant cousins of Earth. Do they have atmospheres at all, or have they been stripped away by their star? If they do, what is their composition? Each observation is a step toward narrowing the search, moving from the question of could life exist to the more direct, does anything live there? The moment we find a truly compelling biosignature will be a turning point in human history, an event that will fundamentally reshape our understanding of our place in the cosmos. The philosophical and cultural implications are staggering. Confirmation of life on another world would mean that the transition from non-life to life is not an impossibly rare fluke, but a common process in a universe filled with the right ingredients. It would suggest that the universe is, in fact, biophilic, teeming with the potential for life. This discovery would instantly transform biology from a science that studies a single example, life on Earth, into a truly universal discipline. We would begin to ask new questions. Is life elsewhere based on the same DNA and biochemistry, or has it found a completely different path? The search for a second genesis would become a primary driver of science and exploration for centuries to come. This profound shift in perspective, the search for life on planets orbiting other stars, naturally leads us to reconsider what a habitable world even looks like, and to the realization that the most promising places for life might not be planets at all, but right here in our own solar system, hidden beneath icy crusts. Just when we thought we understood where to look for life, our own solar system presented us with a stunning paradox. The traditional concept of a habitable zone, that comforting Goldilocks region around a star where water can remain liquid on a planet's surface, has been dramatically upended. We now know that some of the most promising real estate for biology in our entire cosmic neighborhood lies not on planets basking in sunlight, but deep beneath the frozen, airless surfaces of distant moons, kept warm not by a star, but by the gravitational embrace of a giant planet. These are the ocean worlds, and they have transformed our search for life from a distant dream into an urgent, tangible quest. The poster children for this new paradigm are Jupiter's moon Europa and Saturn's moon Enceladus. From the outside, they appear as barren, cracked balls of ice, reflecting the faint sunlight that reaches the outer solar system. But for decades, evidence has been mounting that these icy shells are merely the lids on something extraordinary. The first major clue came from the Voyager and Galileo missions, which revealed that Europa's surface is a chaotic jumble of jigsaw puzzle-like ice plates, suggesting a mobile layer beneath. The gravitational pull of Jupiter and its other large moons creates immense tidal forces, flexing Europa's interior. This constant kneading generates heat through a process called tidal heating, enough heat, in fact, to maintain a global, liquid water ocean trapped between the icy crust and a rocky seafloor. Estimates suggest this hidden ocean on Europa could contain more than twice the volume of all Earth's oceans combined, a vast, dark sea waiting in the abyss. But it was Saturn's small, brilliant moon Enceladus that provided the smoking gun. Prior to the Cassini mission, Enceladus was thought to be a relatively quiet, geologically dead world. Then Cassini witnessed the impossible. Plumes of water vapor and ice crystals were seen erupting from massive fissures nicknamed tiger stripes near its south pole. This was not a slow leak. It was a geyser, actively venting material from a subsurface reservoir into space. In a series of daring flybys, Cassini dove directly through these plumes, its instruments tasting the spray. The results were electrifying. The water was salty like Earth's oceans, and it was rich in simple organic molecules, the carbon-based building blocks of life. Most significantly, the spacecraft detected tiny grains of silica nanograins, which on Earth are typically formed when hot water interacts with rock on the ocean floor. This was the final, critical piece of evidence. Enceladus has a global subsurface ocean that is in direct contact with a rocky, mineral-rich core heated by hydrothermal vents. On Earth, such vents on our deep ocean floors are teeming with life, thriving in complete darkness, powered not by the sun but by chemical energy. Enceladus, it seems, has all the necessary ingredients: liquid water, organic material, and a persistent energy source. This revelation fundamentally shatters the old, sun-centric view of habitability. It means that a planet does not need to be the right distance from its star to host a liquid water ocean. A moon orbiting a gas giant can have its interior melted by gravitational forces. This dramatically expands the number of potentially habitable environments in our galaxy alone. Jupiter's moon Ganymede and Saturn's Titan are also believed to harbor subsurface oceans, and there may be dozens more such worlds orbiting the giant planets of other star systems. The habitable zone is no longer a narrow ring. It is a vast, three-dimensional volume of space that includes the orbital systems of gas giants, a concept sometimes called the subsurface habitable zone. This leads to one of the most thrilling questions in all of science. What kind of life could exist in such an environment? Cut off from sunlight, any ecosystem would have to be chemosynthetic, relying on chemical reactions for energy, much like the communities around hydrothermal vents on Earth's ocean floor. In the perpetual darkness, there would be no need for eyes. Life might rely on other senses, like sensitivity to vibrations or electrical fields. The food chain would be short, perhaps starting with microbes that metabolize hydrogen sulfide or methane released from the seafloor. Larger organisms, if they exist, might be slow-moving, conserving energy in a world with limited resources. They could be pale or transparent, and their biology might be based on solvents other than water, though water remains the most likely candidate. The possibilities are as strange as they are fascinating. We are not necessarily talking about intelligent life, but even the discovery of simple, microbial life on a world like Enceladus would be arguably the most significant discovery in human history. It would prove that life is not a singular miracle on Earth, but a common, robust process that can emerge wherever the right conditions persist. The implications are so profound that space agencies are now actively planning missions specifically designed to search for life on these ocean worlds. For Europa, NASA Europa Clipper mission, scheduled to launch in the coming years, will conduct detailed reconnaissance, mapping the ice shell and studying the composition of the plumes it also appears to vent. The goal is to characterize the ocean's habitability. Even more ambitious are concepts for a future lander that could drill or melt through the ice to directly access the ocean below, perhaps deploying an underwater vehicle, a cryobot, to explore the alien sea. For Enceladus, mission concepts focus on a dedicated orbiter that could repeatedly fly through its rich, accessible plumes, analyzing the material with even more sophisticated instruments, specifically designed to look for complex organic molecules and even potential biosignatures. The dream of diving into an alien ocean, once the stuff of science fiction, is now a serious scientific pursuit. The existence of these worlds in our own backyard, with their tantalizing ingredients for life, makes the cosmos feel simultaneously more familiar and more wonderfully strange. It suggests that the universe may be filled with hidden oceans, each a potential cradle for life, turning our gaze from distant suns to the dark, icy moons that might be the true water worlds of the galaxy. And so we arrive at the final and perhaps most deeply personal mystery on our journey. After exploring cosmic voids, stellar cataclysms, and the hidden architecture of reality, we are left facing a profound silence. It is a silence that speaks volumes, encapsulated in a simple, devastating question famously attributed to physicist Enrico Fermi: where is everybody? This is the heart of the Fermi Paradox. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars. It is also incredibly old, at nearly 14 billion years. The ingredients for life, water, organic molecules, seem to be common throughout the cosmos, as evidenced by their presence in interstellar clouds and on asteroids. Given this staggering scale and abundance, the galaxy should be teeming with life, its signals crisscrossing the void. Our skies should be filled with the traffic of interstellar civilizations, some of which would have had a multi-billion-year head start on us. And yet, when we listen, we hear nothing but a cosmic quiet. When we look, we see no megastructures, no telltale signs of astro-engineering, no visitors. The contradiction between the high probability of extraterrestrial intelligence and the utter lack of any observable evidence for it is the paradox that haunts modern science. One of the most compelling frameworks for grappling with this silence is the Great Filter hypothesis. The idea is that the evolution of life from its basic chemical precursors to a durable, spacefaring civilization is not a smooth, inevitable path. Instead, there is at least one step along the way that is phenomenally difficult to overcome, a barrier so challenging that it filters out almost every species that attempts the journey. This barrier could be a single, nearly insurmountable challenge, or a series of smaller, but still improbable hurdles. The critical and deeply unsettling question is where this filter is located on the timeline of a civilization's development. The answer to this question has profound implications for the future of humanity itself. If the Great Filter lies in our past, it means we are among the exceedingly rare few who have already passed through the bottleneck. Perhaps the origin of life itself, the transition from non-living chemistry to a self-replicating organism, is an event of such staggering improbability that it has only happened a handful of times in the entire galaxy. Or maybe the leap from simple prokaryotic cells to complex eukaryotic cells, which took over 2 billion years on Earth, is the true barrier. Another candidate is the development of higher intelligence and tool use, which, as far as we know, has only occurred once on our planet despite billions of years of life. If the filter is behind us, it is wonderful news for humanity. It would mean we are special, we are alone in our galactic neighborhood, and the cosmos lies open before us. The silence is simply a reflection of our profound rarity. The alternative is far more ominous. What if the filter is not behind us but ahead of us? This is the possibility that should give every person on Earth pause. In this scenario, the development of intelligent life might be relatively common, but the next step, the transition to a stable, technological civilization capable of surviving its own adolescence, is the stage where almost everyone fails. The filter could be the inevitable self-destruction that accompanies the discovery of advanced technology. We have already developed the means to obliterate our civilization with nuclear weapons. In the coming centuries, we may face existential threats from engineered pandemics, runaway artificial intelligence, or climate change on a global scale. Perhaps this is a universal phase. Perhaps every civilization, upon reaching a certain level of technological power, inevitably turns that power upon itself and vanishes. The silence of the cosmos, then, is not a sign of our rarity but a somber cemetery, a warning of a fate that awaits all who dare to reach for the stars. The fact that we see no other civilizations may be terrifying evidence that no one makes it through this gauntlet. This philosophical dilemma forces us to look in the mirror. The Fermi Paradox is not just an abstract puzzle about aliens. It is an urgent question about us. Our continued existence as a technological species, which has lasted for barely a century against the backdrop of billions of years, is a tiny data point. But it is the only data point we have. Every day we avoid a global catastrophe is another day we survive, another day we gather more data. Are we the first to approach the filter, or are we, like so many others before us, destined to become another silent data point in the cosmic census? The paradox imbues our present moment with immense significance. Our efforts to solve global problems, to manage our technological prowess with wisdom, and to navigate the challenges of the 21st century are not just about our own survival. In a very real sense, we are testing a fundamental hypothesis about the universe. We are conducting an experiment to see if intelligence is a sustainable phenomenon or a cosmic flash in the pan. This brings our epic journey full circle, back to the fragile, pale blue dot we call home. After surveying the incredible phenomena that shape the cosmos, from the gravitational pull of the Great Attractor to the accelerating push of dark energy, we are left with a profound sense of humility. The universe is capable of wonders beyond our imagination, but it is also indifferent to our existence. The Fermi Paradox underscores our solitude and our responsibility. It suggests that the value of life and intelligence may not be a common feature of the cosmos, but a precious and fragile exception. The very act of looking up at the stars and asking, "Where is everybody?" is a testament to a unique consciousness that has emerged on this world. Whether we are alone as a miracle or alone as a warning, the silence of the cosmos is a call to cherish our planet, to safeguard our future, and to ensure that the light of our awareness does not flicker and die, but endures to illuminate the darkness. Our tour of these 20 incredible cosmic phenomena has taken us from the ghostly pull of the Great Attractor to the profound silence of the Fermi Paradox, and with each discovery, we have witnessed another chip falling away from our anthropocentric view of the universe. We began by feeling the irresistible tug of an unseen mass, a force guiding the motion of our entire galactic neighborhood, and we ended by contemplating the possibility that we might be utterly alone in the vastness of space. In between, we encountered voids of incomprehensible emptiness, stellar corpses with magnetic fields that can warp atoms from across the galaxy, and explosions so powerful they outshine the combined light of every star. We have seen that the cosmos is far stranger, more violent, and infinitely more beautiful than we could have ever imagined from our tiny vantage point on a pale blue dot. The true value of this journey, however, lies not just in the collection of astonishing facts, but in the profound sense of humility they instill. Each mystery we have explored, from the nature of dark matter and dark energy to the Great Filter hypothesis, serves as a stark reminder that our current understanding is merely a flicker of light in an ocean of darkness. We are participants in a grand, evolving story that began nearly 14 billion years ago, a story whose final chapters are being written by forces we can only dimly perceive. This knowledge does not diminish us, instead it liberates us from the illusion of centrality. We are not the final goal of the universe, but we are a part of it, a species gifted with the rare ability to look up, to question, and to wonder. Let this expanded world, you become a permanent lens through which you see the world. The next time you find yourself beneath a clear night sky, I hope you see more than just familiar constellations. I hope you perceive the invisible scaffolding of dark matter, sense the accelerating expansion driven by dark energy, and remember the hidden oceans churning beneath the icy crusts of distant moons. Let that sight be a catalyst for an enduring curiosity, a personal connection to the great mysteries that still await their solutions. The universe is not a static painting to be admired from a distance. It is a dynamic, unfolding drama, and we have the privilege of being an audience that is slowly learning to understand the plot. The conversation does not have to end here. I am genuinely curious to know which of these 20 phenomena resonated most deeply with you. Was it the haunting emptiness of the Boötes Void that challenged your sense of cosmic order? Or was it the creative fury of supernova nucleosynthesis, the realization that the atoms within you were forged in a stellar explosion long ago? Perhaps the existential weight of the Fermi Paradox left you contemplating our future, Share your thoughts in the comments below. Let's continue this exploration together. And if you're eager for more journeys to the edge of understanding, to delve into the secrets of quantum realms, the mysteries of time, or the search for a theory of everything, be sure to subscribe. Our quest to map the unknown has